Alright, this is the lowest frequencies of a string with varying tensions by jdecker and Walker-Weinstein. And the lowest frequency is the one that you hear. So our observations. So we were noticing the spike of frequency while we recorded the oscillating bars in Audacity. So we wanted a new variable besides the bar size or pretty much the length. So we thought that maybe the tension could alter the frequency in a similar way. Our questions were like, how does the tension in a string affect the frequency of its vibrations? So would it be linear or would it be exponential? That's something we would analyze a little bit later. So our hypothesis was if we test the lowest frequency of a guitar string using 5 different tensions, then we predict that the more applied tension, the higher the lowest frequencies, because they travel at increasing the tension makes the waves travel at higher velocities and increases the vibrations, the frequencies of them. The variables independent are tension, newtons, dependent is lowest frequency in hertz, and constant guitar string length, 18 inches, and maybe torsion. We tried our best to make that constant. Materials: wooden guitar, the string, metal bar and cork to hold the string, spring scale for tension, tablet computer with Audacity. Procedure: so we attached the spring scale to the guitar string, of course, and we pulled the scale until the desired tension was applied on the spring scale in newtons, and record the plucking into Audacity and use the plot spectrum to find the lowest frequencies, and we repeated this for all the tensions. This is a picture of the scenario. You'll see this is where we ran the chord down, and Walker, not really paying attention, but he pulled that down and looked at the spring scale to find exactly the right newtons. This is our data that we got after recording. So we increased it by 5 each time, as you'll see. And these are the frequencies that we got. It'll be graphed in 1 second. Alright, this is the graph. Tension, newtons, frequency, hertz. We applied this line of fit, which we'll talk about more in a second. And yeah, the data seems to go upward, as you'll see. So the line of best fit is possibly correct because it looks more linear than it does exponential. It's not totally for sure. We'll talk about more in the error analysis, but for the most part, yes, as we increase the tension, the lowest frequencies increase. So we predicted just that as we increase the tension, the lowest frequencies would increase. And it supported our hypothesis in the basic sense, in the trend of the data, which was going up. But certain problems with our hypothesis, like we weren't very specific, but we were right in what we predicted, and that means as we increase the tension, we increase the lowest frequencies. So error analysis. Our hypothesis wasn't specific, we talked about that. Our guitar was making unwanted sound, sort of a clangy sound. Our microphones weren't a very high quality mic, and we sort of plucked the strings at a different force each time. So how does the tension come into play while tuning guitars to specific notes, and is there a more precise way to calculate the lowest frequency, and why is the lowest frequency the frequency that our ears can pick up? I made the PowerPoint and built the guitar and collected data. Walker also collected data and helped with the guitar. Alright, this has been Inquiry Lab for the lowest frequencies, and I hope you liked it. Thanks.